So when I talk about my work, I usually spend quite a bit of time motivating it by telling stories about bugs, computer security, critical systems, and so on. And sometimes there's even a picture of a rocket blowing up. And thankfully, if you've come to watch a talk about verification of PLDI, you probably don't need 15 minutes of me ranting about bugs. So for this talk, I'm going to just cut all this out and get to the point. I like to think of bugs as falling in roughly two categories. There's programming mistakes, which are low-level bugs, like out-of-bound accesses, or null dereferences, or integer overflows, or use after freeze. And then there are logic mistakes, which are errors in the implementation of the business logic, cases where the implemented functionality of the software does not line up with its creator's original intent, like incorrect information flow, or incorrect access controls, or broken algorithms. Now, if I put programming languages on an axis from low level to high level, the usual suspects of system implementation tend to cluster towards the bottom, and they tend to be vulnerable to both kinds of bugs. But it turns out that we've known for a long time how to fix those low-level bugs, or at least how to mostly fix them. We have many programming languages that completely rule out these issues. We call them high-level languages, and they come with high-level abstractions that are intended to make programming easier and less error-prone. So not only are high-level languages designed to rule out all sorts of low-level bad behavior, they're also intended to help minimize logic bugs and implementation mistakes. Some of the purest embodiments of these ideal are functional languages, and if you push them to the extreme, you get so-called purely functional programming languages, which lend themselves nicely to mechanized reasoning and program proofs. Now, if purely functional languages and proofs rule out all sorts of bugs, then why aren't we using these languages everywhere? And well, one big issue with this is performance. High-level functional languages, they encourage a programming style that is safe and easy to reason about, but also relatively inefficient. And as a result, the uptake of functional programming in critical systems has been very slow. So we have a gap. We'd like to write software in high-level languages and verify it, and we'd also like to run the result with great performance. And since we can't do both, we're stuck with either efficient but tricky to write low-level imperative programs, or slow but nice to write high-level functional programs. And this is precisely what this talk is about, creating methods to transform high-level functional programs into efficient low-level ones. The goal is to match the performance of handwritten low-level code, but without the risks and costs of writing that code by hand. Let me give you an example. We'll start with a very simple program. So assume that I'm writing, say, a DNS server, and it's tasked with translating website names into IP addresses. Now, a DNS server is basically a packet parser and then a database in the back. So you get a network packet as input with a domain name string in it. And DNS is not case sensitive, so the first thing you have to do before you can look up that name is to normalize it, let's say by converting it to uppercase. So what I've shown on this slide is a absurdly short yet completely functional implementation of this task in the programming language Coq. Now, this program is short and sweet, and I can trivially prove interesting properties about it. And the nature of the language means that it's impossible to write all sorts of low-level bugs like excess memory memory access problems, mistakes while manipulating pointers, things like that. It's a lovely bit of code, but now let's compare it to what a fast implementation of this task might look like. If you're dealing with ASCII strings only, and if the original string is never reused, then a good choice would be to represent the input as a struct, containing a length and a pointer to a contiguous array of characters. And as a bonus in ASCII, uppercasing a character is just a matter of one comparison and one bit flip. So on the left, we have the pure functional implementations, which recurses over a linked list of characters, and it creates a new list. And on the right, we have the efficient mutating for loop. Now here's a question. Could a general purpose compiler take the version on the right and generate the code, the version on the left, and generate the code on the right? And the answer is just no. For starters, the compiler could not guess that it's safe to mutate the string in place, so it would have to assume the worst and produce slow code. It would pointer chase their linked list, which creates data dependencies, cache pressure. It would build a fresh string, which costs allocations, cache misses, and extra traversal for garbage collection in certain cases. It will either stack overflow on long strings or traverse the string twice, doubling allocations and pointer chasing costs. Or it will accumulate continuations, costing even more allocations. And for each character of the string, it will allocate a const cell and jump through a branch table to determine which uppercase character to put in the output. Now compare that to the C version on the right. It performs a single pass. It occupies constant stack space. It does not allocate. It's cache friendly. It can be unrolled. It's trivially vectorizable. Now, it's hard to benchmark tiny functions like this, but there's easily a factor 30 to 15 efficiency between typical compiler outputs on these two programs. You don't even really have to run the code to check this. A quick glance at the assembly tells you all you need to know. Bridging this gap is what this talk is all about. It's about building a compiler construction framework that lets you compile a functional program on the left to the imperative one on the right. Before I tell you everything about our solution, though, I'd like to situate this work a bit in the broader context of how people connect their specifications to executable code. So going back to this taxonomy, the first approach is extraction. When performance is not a critical concern, people verify code in languages like Coq and then generate executable code from it, which can then be compiled and executed. At the other extreme, when performance matters a lot, people sometimes write code directly in a lower level language and verify it with specialized tools like VST, VCC, Daphne, and so on. Finally, instead of reasoning directly on the low level code, people have also designed converters and translators that take a program and lift it into the logic of another language, for which better reasoning tools exist. As in Goose for Go, or CFML for OCaml, or HS2Coq, or if my Twitter didn't lie yesterday, ANIAS for translating Rust into functional models. But beyond performance, there's another issue to consider, and that issue is trust. All the little arrows I drew and most of the tools that I showed on the previous slide are not verified, so you have to trust that your translator is sound and that it won't introduce its own bugs. And that's why I drew them all in red. That's why relational compilation, the concept that we push in the paper, helps. It's the technique that Rupicola, the project, that the relational compilation framework that we built, is built on. And it's a proof-producing way to perform code translations. So it enables new trustworthy arrow, like the two that I just added to the picture in green. One pre-existing and one the Rupicola framework itself. So to solve the problem of extracting high-performance, low-level implementations from functional programs, we built Rupicola. It's a relational compilation toolkit that lets you build customized compilers. The key to our solution is to give up on having a single compiler. Instead, we enable users to create one small compiler per problem and per domain, and even sometimes per program. Rupicola works by replacing monolithic translation functions between languages by small, composable, and extensible objects. Rupicola is designed so that it's easy to plug in new tricks into a compiler without jeopardizing its overall correctness. In the example above, we'll teach the compiler first to recognize the case where the string is not reused and to recycle its storage in place. And then we'll teach it to store the string in a contiguous fixed-length array of native chars. Here's a general pipeline from high to low-level code, which shows roughly where Rupicola fits. So if you have high-level specifications, we let you use whatever technique you want to produce a lowered model, but still purely functional, that is closer to the kind of code that you want to get. This is this first step from the top left to the top right. Then you use Rupicola to generate equivalent low-level imperative code. Then you use a regular verified compiler, ideally verified compiler, from this imperative language Bedrock 2 that's developed at MIT to assembly and then machine code. Now, crucially, there's two things here. First, Rupicola is not one compiler. It's a toolkit to create custom compilers. Second, the result will be very domain-specific compilers. We don't want and we don't need to support every program. We're only trying to compile certain programs. And for these, we want to get really good performance. The key idea in Rupicola is that we can recast each compilation task in terms of proving a theorem. So concretely, a typical compiler is a function from some language A to some language B. That function is correct if it produces outputs that have the same semantics as the inputs. Having such a function is the same thing as having a proof that for all A's, there is a B with the same semantics as the original A. That's essentially Skolemization. But if you have a specific program in hand, if you're not interested in compiling all programs, then all you need to do is compile that one program. And then you don't need a function that handles all A's. You just need a proof procedure that, given one specific A, is going to prove the existence of a B. This paradigm shift from producing one function that can compile all programs to producing a proof strategy that infers programs one at a time is the thing that makes Rupicola work. Specifically, for each program that we want to translate with Rupicola, we state a theorem that says there exists a low-level program which, given the right arguments, produces the same output as the original functional program. So bear with me while we read this theorem together. We say that there exists a program such that for all inputs, so those are high-level values, and for all machine state or memory state M, if the input is stored in the machine at address input, then for all machine state reachable from the original machine by running the program, the machine state at address output contains the value that we're expecting, f of a. Proving this theorem is the same as correctly compiling the function f. Equivalently, what we do to compile a program in Rupicola is prove that a given Hoare triple is inhabited by a little program prog in the middle here. To do that, what we do is we combine individual lemmas, which are each responsible for relating one functional programming construct to one imperative construct with a bunch of side conditions that clarify when those transformations are applicable. The paper has a long tutorial on relational compilation. In fact, there's an even longer version of it in my thesis. But this talk does not have a long slot for me to do that. So I will skip through this and I'll just demonstrate directly on an example that Rupicola handles. So remember when I mentioned that we were going to compile a function that uppercases a string. So that's what we're seeing here. You see at the top, you have there exists a program, and then we quantify over all input strings. And then we say, well, we have two variables, one that contains the string called s, and then the one that contains the length of the string called len. And then in the output of the program, we want to store in the same variable the result of uppercasing the string. and the length should be unchanged. Now, all this process is going to be automated, right? So Rupicola does all this automatically. Um, but I'm going to step you through what it actually does. So the first thing it does is introduces a little hole that we're going to plug in by constructing the program progressively. Then it recognizes the map pattern. So there's one rule that the user plugged in that says, hey, if you see a map, transform that into an iteration. So we replace this by starting with an index at 0 and then iterating from 0 to the length of the string. Now we split this in two. The first part is finding a way to set something to 0, and that's pretty easy. We have a lemma that tells you, hey, in low-level code, just assigning to 0 is assigning to 0. And then for the second part, now we get to assume that index is 0. You see that in the precondition of the program. We have a lemma that says iteration can be broken into two parts. First is at the bottom, putting in the template for a loop. And second is inferring the body of the loop. And the body of the loop is now quantified on the particular index that we're looking at. And now we break down the part about reading a character, uppercasing it, and putting it back. We break this down into 3 steps. First, we read the string, and then we have a lemma that says, hey, reading from a string is the same as reading a pointer. Second, we uppercase the character, and here we have a lemma that says, hey, an efficient way to uppercase a character is actually just the comparison, the bit flip trick that I was mentioning earlier. And finally, writing into a string is just a matter of updating a pointer. And so under the hood, Coq is keeping track for us of the program that is being built. So it starts being empty, and then progressively we first set an index to 0, then we have this while loop, and then we construct the body of the while loop step by step, first reading, and then uppercasing, and then writing. Rupicola's unique strength is its combination of foundational proofs, extensibility, and high performance. There's 2 particularly innovative aspects of Rupicola that might be worth mentioning, though the paper actually goes over them in much more detail, or in some detail at all, really. First, it uses a trick to encode loop invariants so that they can be inferred and all reasoning can happen on the source language. So you never have to reason about loops in low-level terms. And second, in many cases, it can introduce mutation and other effects without having to rewrite the source in monadic style. And when you do want to use monads, if you do have to actually use monads, then we also have tricks to save you development costs. So I said that Rupicola was designed to be sound, extensible, and fast. And these are the axes against which we evaluated it. The first one is soundness, and here we just did everything inside of the Coq proof assistant so that all derivations that Rupicola produces are actually checked by Coq's kernel. Extensibility and modularity of fuzzy concepts, so we use mostly case studies. And then performance is easier to evaluate. You can just take C programs, rewrite them in Rupicola, compile them back, and then measure the result performance. We focused on small performance critical functions that appear in string processing, data structure, network functions, and so on. So let me go briefly over what all these benchmarks look like. The micro benchmarks is essentially a bunch of small functions that we generate code for. Introducing new operations means introducing new source patterns, new monads, new data structures, new operations on these data structures. Low-level code patterns is plugging support for features of the low-level language, like stack allocation or inline tables. We did a case study where we replaced one part of Rupicola that had been implemented as a reflective compilation procedure, and we changed it for a relational compilation procedure, and it became much, much, much easier to think about and implement. And finally, we did an end-to-end case study on a network function where we start with a high-level specification, lower it into a manually with proofs, but the proofs are very simple, into a lower-level functional implementation, and then actually compile it with Rupicola to imperative code and benchmark it. Speaking of benchmarking, here are some benchmarks that we actually did. So what you see in brown and orange and yellow tones are Rupicola's times. So you generate C code with Rupicola and then you benchmark it. And then in blue and purple, you see the equivalent handwritten code. And what we see is that, and this is over multiple different compilers. Right. And what we see is that for most examples, there's very little variability across compiler versions and between Rupicola and the handwritten code. There's one thing I would like to mention, though, and it's the fact that there's something that's always a bit tricky when you compare the performance of a tool to handwritten code. Because, well, you can always rewrite handwritten code to actually make it match the output of your tool. Your tool is producing C code, and this is handwritten C code. Now, of course, it's not fair to do that if the handwritten code is faster than what Rupicola generates. But in a sense, it is fair to do that if the handwritten code is slower, because any code could be handwritten code. And in fact, this happened for one of the examples in this chart. We rewrote the example of Rupicola. It yielded more efficient code in C. And so we just then rewrote the handwritten C so that it would match the performance of Rupicola. I want to stress that last point a bit. In a large number of cases, Rupicola is going to produce code that's completely equivalent to a handwritten C version. And hence, you'll see absolutely no performance difference because you'll be running essentially the same assembly code. And of course, that's a bit muddied by the fact that C compilers are unstable. But if you want to hear me rant about C compilers, find me after this sequence. All right, let me zoom on one specific example. Here I have Rupicola and I have C, and they're very comparable. But there's another way to compile calc code, right? Because we started with calc code. This is the end-to-end example. You can also extract to OCaml and then generate OCaml code and compile it. And yeah. So this is the same graph showing OCaml. And well, okay, so it's flashy, but it's not very surprising because of all the overheads that I mentioned earlier. And it's really not OCaml's fault. It's faithful to the original high-level inefficient program. It was really a spec. It was not an efficient program that we started with. So it's normal that it runs really poorly. The C version, on the other hand, is quite optimized. In fact, it's not even really meaningful to measure the kind of speedups that I showed on this graph here, because the asymptotic complexity of the code that we generate in C is not the same as that of the original specification. All right, to summarize the big picture idea and conclude, it is possible to use proof assistance to build extensible compilers that are sound, flexible, and generate code with uncompromising performance. The key is to think of compilation as proof search and to think of cross-language transformations as individual theorems that make progress in the proof of a theorem that says there exists a low-level implementation of this high-level program. There's plenty of related work. I won't have much time to cover it, but our contributions include generalizing the input language, allowing more flexibility in designing the input DSLs, targeting a language with a garbage collection, deriving end-to-end proofs, generating fast code, and doing this interactively in a proof assistant. Now, this concludes the presentation. Beyond the concrete artifacts that we produced, I'm particularly excited about this line of research because it's a case of proof assistance enabling new technology, not doing just proofs. So if you want to work with me on these topics, please come find me and let's chat. I'm recruiting students and postdocs as a PFL, and I also have cool compiler work going on at AWS right now. Thank you very much.
Thank you. Okay, very good. So we have time for 2 or 3 questions maybe. And if you do have a question, maybe come forward a little bit.
So what kind of a data structure you have tried? It sounds like the example you show is just a string, right? Array.
That's right.
Would it work on more sophisticated?
Yeah. So we have some ongoing work on more sophisticated data structures. There's all sorts of interesting questions that pose themselves when you start dealing with structures that own pointers to other sorts of structures. For now, most of the structures we've dealt with are in the end backed by arrays in the low-level program and lists in the high-level program, a variance of lists.
Okay. Anybody else? So a question that I had was, you compared the input and output programs along a variety of criteria. What about readability, maintainability, or something like that of that final low-level code that you produce? Could a human pick that up and do something with it?
Definitely not right now.
Definitely not right now.
The output is not exactly readable.
Okay.
And in fact, some of the output will compile correctly if you pass the right flags to your C compiler, but otherwise is a bit iffy. So the story is that we have really two backends. The right way to use Rupicola is to compile to Bedrock 2 and then use the verified Bedrock 2 compiler that generates machine code, and then you have an end-to-end pipeline. The realistic way, or the more pragmatic way, if you want really good performance, is to use a traditional compiler like GCC. And so we have a little pretty printer that is not verified that goes from Bedrock 2 to C programs. And there's been absolutely no efforts on readability for this. And I would argue that it would be a bad idea to invest in readability for that, because every effort you're going to make there is in an unverified tool that you're going to make more complicated for the purposes of making it more readable, despite the fact that it was originally verified.
Great talk. So you said these rewrites can be done compositionally. Can you say more about sort of the art of how you pick these things and stitch together the reasoning of the overall compilation?
Yes. So it's a natural worry to be thinking, well, there's going to be many of those, and maybe at some points there's multiple that apply, and so how do I pick which ones? But in reality, what typically happens is that it's not that there are many that apply, it's that there are none of them that apply. Because you start from a blank slate where you can compile nothing, and then you plug in some of these things. Now, even for that, if you compile a list as an array in one case, and then the list as a hash table in another case or something, there's going to be something smart happening there. What we do is that we use aliases of function names in the source to indicate what you want. So we have a module called array list, which is just really module array list equals list. And then we have a module called, I forgot the names, whatever. But we have multiple of those that are just transparent aliases so that you can expand them, and then your verification is just as easy. But then the compiler doesn't have to guess. We try to make the compiler as not smart as possible.
So if these kinds of rewrites are extensible, like the trick for knowing how to translate, for instance, uppercasing a character, and like the user can provide any rewrites that they want. What part of the system is responsible for verifying that the rewrites are implemented correctly? Like that's complicated C logic was correct, and how much work is it to do that? Like who is expected to do that in the ecosystem of this language and so on?
So I think it helps to think of the system as having 3 tiers of users, right? There's the developers of Rupicola itself, that's us, and it's a small group. Then there's developers of rewrite rules, and those are the people implementing support for new domains or new kinds of programming in Rupicola. And these people need to do reasoning. They're responsible for the correctness because what they're proving is not just when they're providing is not just when you see this pattern, generate this program. What they're proving is, and by the way, these 2 things that I just mentioned are related. They have the same semantics. So they're providing proofs in addition to rewrite rules, essentially, or transformation rules. And then there's a third class of user, which is just people writing the actual code. And these people, they just leverage existing limits.
Got it. Thanks.
I suggest we take the last question offline because I don't want to derail the next talk.
Okay, so my question is, have you encountered a case where you cannot rewrite your high-level functional program into the low-level one in many small steps that requires a single large step?
Yeah, so non-local control flow is a good example of this. This works very nicely if you're mapping, if your transformations are very local. But if you have things like exceptions or long jumps or things like that, arbitrary go-tos, those are basically hard to handle in this. And the recommendations there would be to handle them through traditional same language rewriting strategies, as is done in traditional verified compilers. Thanks. Thanks, everyone.
Okay, thank you. Let's thank the speaker one more time.